Hi, this is problem 4, the activity of Ziegler-Nichols and ITAE approximations for designing PI compensators. For the first activity or problem, I will present problem 1, 2, and 3 of the activity in this video. For the first problem, we were asked to use a Ziegler-Nichols algorithm to obtain a first order approximation of the system with the following unitary step response. We have this graph, and we can obtain some values by finding the maximum slope of that curve. And in the first like point of the maximum slope, we get we draw a vertical line, and we can intersect that with the time, and we can obtain the value of L, that is 0.1 in this case, and we do the same in the intersection of K and the maximum slope, that in this case K is equal to Ka because of the unitary step. We get that value of 10.1, and we knew this value of K equals 10. In this case, we have this formula of the Ziegler-Nichols, and we just substitute that values on that formula, and we get this one. We get these values or this transfer function, and that's all for the first problem. For the second problem, we were asked to make a PI compensator, not P or PID, considering the Ziegler-Nichols tuning criteria for the system 1. We had this formula taken from a book of control, and we just know that the integral part is equal in the domain of S of a division of S, and the derivative part is equal to multiply some terms times S. Okay, I think this is it's an error, but just an error of the formula. This one is equal to the E part of this, and the Kp remains equal, but we have this now in the domain of S. So we have a table with some values for designing a PI compensator. That is, this row is the one that is important to us, this row. So we just know that the value of Kp is equal to 0.9 times this over L, and the value of Ti is equal to L over 0.3, and the value of Td is equal to 0. So we just get the values from above of the first problem, and we just substitute that in the transfer function formula of the PI compensator, and we get this. So for the third problem, we were asked to design a PI compensator considering the ITAE tuning criteria of the system 1, and we have this formula, but we'd rather use this table taken from a book also, but we don't take the value of Td, since it's a PI compensator, not a PID compensator. So we remind that the value of L was 0.1. We remind that the value of T is 10.1, and the value of K was 10. So we now have these formulas from for Kp, for Ti, and for Td that we will not use it. And we just substitute values for taking the values of Kp, Ti, and well, Td is not used. So we just substitute the values that we have above and obtain the value of Kp, the value of Ti, and the value of TD is not used, so it's 0. If we use that, we will have this value from here and just add it to the transfer function, but since it's a PI compensator, we will not use it. So we get this result, and we will use these results for the next step of the activity.
Well, this is the problem for the PI compensor transfer function is the following. That is ds equal to kp multiply s plus 1 between ti between s. Simulate the step response of the closed loop system with the compensor design in the problem 2 and the problem 3. With the following process, plan the transfer function. And ds is the transfer function used to obtain the graph in the problem 1. You can obtain the transfer function of the whole closed loop system by hand, or you can use the instruction feedback in MATLAB. And the formula of ds is 1 between s plus dot 2 multiply s plus dot 5. The first thing that we need to do is to obtain the block diagram. That is that. Then when the theorem of the diagram, we obtain this formula, that is ds between 1 plus ds yes. Then we substitute this value, that is ds, and this value, that is es. To obtain ds, we substitute kp, that is 90.3, no, .9, and the ti, that is 1 between 3. Then we multiply the 90.9 for s plus 1 between 3, and we obtain 90.9 s plus 39.3. Then we divide this formula of s, and we obtain this formula. This formula is the formula. Then we multiply this formula, that is ds, with this formula, that is ds, and we obtain this formula. Then we substitute in the first formula, that is this, the value of ds and gs, and we obtain this formula. And with algebra, we obtain the result of the transfer function, that is 30.3 s plus 90.9 between s squared plus 31s plus 9.98. And this is the simulation in MATLAB. This is the result. This is the graph. And with the problem 3, we do the same. We obtain the block diagram and the same formula. Then we substitute kp and ti. The kp is 4.84, and the ti is 1 between minus .73. Then we multiply the 4.84 for s plus 1 between minus .73, and we obtain this formula, that is ds. Then we divide and obtain the formula, and multiply the ds and the gs to obtain this formula. And then we substitute this formula in the first formula, that is that, and we obtain this formula. And then with algebra, we obtain the formula, that is the transfer function, that is minus 6.61s plus a4 between between s squared minus 5.91s plus 4.98. And this is the simulation, and this is the graph in MATLAB. And the problem 5, say the position static error. This is the formula: P minus equal to limited when s is equal to 0 or yes. The result of this, we we know that this is a type 1, and the static error constant of the of Kp where is infinite because it's a step function, and the static error is equal to 0.
Okay, so here we need to get the speed static error, and we got a g of s function, so we need to tend the s in this function to 0. So if we make this value 0 and 0 and 0, we would get 90.9 over 4.98, and the result would be 18.25. And then we continue in this part. We got that the static error is 1 over the constant value, and we get that the static error is 0.05479. And then we go to the we needed to do 2 examples, and here's the second one. Here we have the same steps. Here we have the g of s function. We tend it to 0, and we get this value 0.9718. And then we do this division 1 over 0.9718, and we get the value of 1.0029. This is how you get the static error of the velocity. And then we will continue to the acceleration static error, and I hope this image is big enough. So we have our our system that is a type 1, and in the type 1 we have the different inputs and the static errors that it has. So in this case we have a type 1, and the constant would be 0. And if you remember, the formula to get the static error is 1 over the constant. So in this case 1 over 0 would be infinite, and that is how you get the acceleration static error.